We're really good at finding patterns in numbers. It's easy to see how something like height and weight might be connected. But what about the stuff we can't measure so easily? Things like people's opinions, or their preferences, or even their habits. How do you prove a real mathematical connection there? Well, in this explainer, we're going to dive into a super powerful statistical tool designed to do exactly that, to find relationships in a world that goes way beyond simple numbers.
So, let's start with a practical question. Make it real. Imagine a company launches a brand new shampoo. They start getting feedback, but they need to know, is that glowing review from a teenager just a random one-off? Or do younger people genuinely like this product more than older folks? Is there a real, provable link between age and opinion?
Okay, first things first, we need to get a crucial distinction out of the way. You've probably heard the word correlation. That's for connecting two things you can measure with a ruler or a scale, like height and weight. But what we're talking about today is association. This is a totally different tool, and it's built specifically for categories. Think opinions, excellent, good, fair, or voting habits, or any other attribute you can classify, but not just measure.
To find an association, you can't just stare at a pile of survey responses and hope for the best. We need a system. So our first step, let's call it Act I, is all about getting these attributes organized in a way we can actually work with. And our number one tool for this is the contingency table. Now, don't let the fancy name fool you. It's really just a simple grid. But it's an incredibly powerful one. It lets us take that whole mess of opinions and neatly organize them by crossing one attribute, like age group, with another, like a product rating. It's how we turn chaos into a clean, structured picture.
And boom! Here's exactly what that looks like in action. Using our shampoo example, this table shows us the raw counts. This is what we actually saw, so we call it the observed data. We can see right away that 18 people in the 15 to 20 age group rated it excellent. But just looking at this, a big question pops up. Are these numbers actually meaningful, or could they have just happened by chance? This table, it's just our starting point.
Right, so just looking at the numbers we have isn't enough. How do we know if they're significant? Act 2 is where the real magic of statistics comes in. We have to compare what we actually saw with what we would expect to see if the whole thing was just pure random chance.
And to do that, we start with a fundamental idea in statistics, the null hypothesis. The best way to think about it is like the innocent until proven guilty principle in a courtroom. We start by assuming there is absolutely no connection, no relationship whatsoever between our two categories. So for our shampoo data, the null hypothesis is simply age group and shampoo ratings are totally independent. Our job now is to see if we have enough evidence to prove that assumption wrong.
And this leads us to the most important question of our entire analysis. If that null hypothesis were true, if there were zero connection at all between a person's age and their opinion, what would this table of numbers actually look like?
And here's the cool part. We don't have to guess. We can actually calculate it. These theoretical numbers are called the expected frequencies, and there's a simple formula for it. For any box in our grid, you just multiply its row total by its column total, and then divide by the total number of people in the survey. This calculation paints a perfect picture of a world where there's zero connection, where everything is completely random.
And here it is. This is what that no connection world looks like for our shampoo data. Now we can compare. In the real world, we observed 18 excellent ratings in that 15 to 20 group. But in a perfectly random world, we would have expected 20.31. You see the difference? Our entire analysis now boils down to one thing: measuring the total size of the gap between these two tables, the gap between reality and random chance.
So how do we measure that gap? How do we put a single number on the total difference between what really happened and what would have happened by chance? Well, that brings us to our final act. Let's unveil the mathematical tool that does exactly that.
Meet the chi-square test. Its entire job is to calculate one single score that represents the size of the difference between our observed table and our expected table. In a nutshell, it tells us if the patterns we're seeing are real and statistically significant, or if they're probably just a fluke.
Now, don't let the formula scare you. The idea behind it is actually really simple. For every single cell in our table, it finds the difference between what we saw and what we expected, squares it, and then scales it a bit. And then it just adds up all those little surprise scores to give us one grand total chi-square value. A bigger value means a bigger surprise, a bigger gap between reality and chance.
Okay, one last piece of context before the verdict. To figure out if our chi-square score is big enough, we need to account for the size of our table. And that's where degrees of freedom comes in. Think of it this way. A bigger, more complicated table has more room for random weirdness to happen.
This simple calculation, just rows minus 1 times columns minus 1, tells us exactly how high to set the bar for significance. All right, we have all the pieces of the puzzle: our observed data, our expected data, and the test to measure the difference between them. Let's get to the climax and see how it all comes together. We'll switch to a classic example to see how we get to a final verdict. Let's raise the stakes a bit. We can apply this exact same logic to a classic question in political science. Is there a statistically significant association between a person's gender and their voting preference?
So, we go through the exact same process, build a contingency table, calculate all the expected frequencies, and then run the chi-square formula. For this data set looking at gender and voting, our final test score comes out to 16.2.
But is 16.2 a big number? Is it big enough to mean something? This is where our degrees of freedom come in. For a table of this size, at a standard level of confidence, the critical value, the threshold we have to beat to say our result is significant, is 5.99. And here is the moment of truth. Our test score is 16.2. The threshold we needed to beat was 5.99. It's not just a little bigger, it completely blows past it. We didn't just clear the bar, we soared right over it.
And there it is, our verdict. The gap between what we observed in the real world and what we'd expect from random chance is way too big to be a fluke. Because of that, we can confidently reject the null hypothesis. We've proven it wrong, and we can conclude that yes, in this dataset, there is a statistically significant association between gender and voting preference.
This quote really sums up the power of what we just did. This test lets us go from a hunch to statistical certainty. It lets us prove whether a link between two categories is real, and this has enormous implications in the real world. You know, in really high-stakes fields like medicine, proving if there's a link is just step one. Researchers often need to know how strong that link is. And for that, they might calculate something called an odds ratio. It's a number that tells you exactly how much more likely an outcome is for one group compared to another. Just take a look at this powerful real-world example from a medical study in France. Researchers used this exact logic to test for an association between high alcohol consumption and esophageal cancer. The results were absolutely staggering. The calculated odds ratio was 5.5. That means the high consumption group had 5.5 times the odds of developing this cancer compared to the low consumption group.
And that really brings us to our final thought. As we've seen, the association of attributes isn't just some abstract exercise in a stats textbook. It's a tool that can uncover life or death connections that are hidden in the data all around us. Which leaves us with a pretty critical question. Once we can mathematically prove a link between a human habit and a deadly disease, what is our responsibility to act on that knowledge?